Your database can lie to you, even when every single query succeeds. As we dive into the source material for this explainer, I was caught completely off guard by a bold truth. You might think your data is perfectly safe, but under the hood, a completely different story is unfolding.
It turns out, ACID has unfortunately become mostly a marketing term. We've all been there, right? We wrap our application code in a database transaction block, hit commit, and we just assume perfect, impenetrable safety. But distributed systems theory tells us a much darker truth. Under heavy concurrent load, when thousands of users are hitting your system simultaneously, the database starts making compromises. Compromises you never actually asked for, and compromises that can silently corrupt your data without ever throwing a single error.
Today, we're exploring exactly how this happens. We'll uncover the great database lie, the perils of weak isolation, the collision of lost updates, write skew and phantoms, the fix known as serializability, and finally, the illusion of perfection.
Okay, Section 1. The Great Database Lie. We all blindly trust the acronym ACID, don't we? But the reality is quite different. In the database world, atomicity doesn't mean multi-threaded concurrency safety like it does in regular programming. It literally just means abortability. If an error occurs halfway through multiple writes, the database throws everything away so you can safely retry. Consistency? That is entirely your application's responsibility. The database doesn't know your business rules. If you write bad data that violates your own invariants, the database won't stop you. Durability just means once it's committed, it's safely on disk. But isolation? Isolation is where the big lie lives. Isolation promises that concurrently running transactions won't interfere with each other. But true isolation is almost never what you get by default. Moving to Section 2, the perils of weak isolation. So why do databases lie to us about isolation? It all comes down to trading safety for speed. True, perfect isolation means executing every transaction sequentially, one after the other, but that is incredibly slow. To boost performance, databases default to weak isolation levels. Let's start with the most basic default in many popular databases, read committed. Read committed makes a simple promise. It guarantees you won't see data that hasn't been committed yet, preventing a dirty read. And it guarantees you won't overwrite data that hasn't been committed yet, preventing a dirty write. Sounds pretty safe, right? Well, let's look at what happens if you don't even have that.
This brilliantly illustrates why preventing dirty writes matters. Imagine a used car website where Alice and Bob are simultaneously trying to buy the exact same car. Buying this car requires two distinct database updates. First, updating the website listing with the buyer's name, and second, generating the sales invoice. Without protection against dirty writes, Bob's transaction might successfully update the listing to show he is the buyer, but Alice's transaction might sneak in and overwrite the invoice table. The result? Bob officially gets the car on the website, but Alice gets the bill. Read committed prevents this specific disaster by locking the rows until the transaction finishes. But, as we're going to see, read committed is nowhere near enough to guarantee real safety.
Imagine a bank transfer happening exactly while you are reading two of your account balances. Let's say you have $1,000 total. You read account 1 and it has $500. Just then, a background transaction transfers $100 from account 2 into account 1. Then, your read continues and checks account 2, which now has $400. You look at your screen and see $500 plus $400. It looks like $100 just vanished into thin air. You'd probably panic. This timing anomaly is called read skew, or a non-repeatable read. Read committed completely allows this to happen because it only cares that the data was committed at the exact millisecond you read it. It does not guarantee a consistent view across your entire transaction.
To fix this vanishing money problem, databases step up to the next level, snapshot isolation. And they achieve this using an incredible technique called multi-version concurrency control, or MVCC. Instead of locking rows and killing performance, the database just keeps multiple committed versions of an object side by side. Every transaction gets a unique ID. When a transaction deletes or updates a row, the old row isn't actually destroyed immediately. It's just marked with a deleted by tag for that specific transaction ID. This allows a magical performance boost. Readers never block writers, and writers never block readers. A long-running analytics query can essentially look at a perfectly consistent photograph, a snapshot of the database from the exact moment it started, completely ignoring all the frantic writes happening around it.
All right, Section 3, the collision, lost updates. Let's see how things break down when we stop just looking at read anomalies and introduce concurrent writers updating the exact same data. This creates a massive, frequent collision known in the industry as the lost update. Picture two e-commerce clerks concurrently adding stock to the exact same inventory item. This is the classic read, modify, write cycle. Clerk A reads the database and sees 5 items. Clerk B reads the database at the exact same time and also sees 5 items. Clerk A adds 1 to their local count and writes 6 back to the database. A microsecond later, Clerk B adds 1 to their local count and also writes 6 back to the database. Even though 2 items were added to the physical warehouse, the database only recorded 1. The later write completely clobbered the earlier one. This is a lost update, and trust me, it happens constantly in distributed systems.
Fortunately, I was incredibly relieved to learn that backend engineers have a few robust tools to prevent lost updates. First, you can push the math down to the database using atomic operations, like telling SQL to literally set count equals count plus 1, skipping the read step entirely. Second, you can use explicit locking, like appending for update to your select query, which forces other transactions to wait in line. Third, some databases automatically detect this collision in their higher isolation levels and will actively abort the second transaction. And finally, you can use compare and set loops, where the update only succeeds if the data hasn't changed since you last looked at it.
Moving into Section 4, Write, Skew, and Phantoms.
Prepare yourself, because if you thought you were safe now, you are wrong. There is a much more insidious bug that slips right past snapshot isolation, completely ignores atomic operations, and requires absolute mastery of concurrency to spot. It's called write skew. Let's look at the famous doctor's off-call race condition. Imagine a hospital booking system where the strict business rule is there must always be at least one doctor on call. Alice and Bob are both on call. Suddenly, they both feel sick at the exact same time and concurrently hit the Go Off-Call button on their apps. Alice's transaction queries the database. How many doctors are on call? The database answers, 2. Since 2 is greater than 1, her transaction decides it's safe to update her status to off-call. But simultaneously, Bob's transaction asks the exact same question. The database again answers, 2. So his transaction also updates his status to off-call. Both transactions commit successfully. They didn't overwrite the same row, so there was no lost update. But incredibly, the hospital is now left with absolutely 0 doctors on call. The application invariant was completely destroyed.
This happens because of something called a phantom. A phantom is when a write in one transaction changes the search result of a query in another concurrent transaction. In the hospital example, the transaction made a decision based on a premise. There are 2 doctors on call. But by the time the write actually occurred, that premise had vanished. The facts literally changed under their feet. Write skew is the ultimate proof that your database isolation is, in many ways, an illusion. Which brings us to Section 5, the fix, serialization. So, how do we actually fix this? Write skew proves that unless we intervene, the database will fail us. But researchers have a fix that prevents every single race condition we've discussed so far, from dirty writes all the way to phantoms. That fix is serializationality. Serializationality is the absolute gold standard of isolation. It guarantees that the end result of your database operations is exactly the same as if every transaction ran sequentially, one at a time with 0 concurrency. If your code is correct when run alone, it'll be correct when run concurrently, period. And under the hood, modern databases achieve this using 3 distinct methods. I was surprised to learn that for decades, the standard way to achieve this was two-phase locking, or 2PL. Now, contrast this with snapshot isolation, where we said readers never block writers. With two-phase locking, readers do block writers, and writers do block readers. If you want to read a row, you take a shared lock. If someone wants to write to that row, they must wait for you to finish reading. It provides perfect, bulletproof safety against write skew and phantoms. But the cost? Performance plummets. Under heavy contention, your application will grind to an absolute halt, waiting on locks. But there is a modern, brilliant alternative, serializable snapshot isolation, or SSI. This is an optimistic concurrency control technique. Instead of aggressively locking rows and killing your performance, SSI lets transactions run normally using standard snapshot isolation. But, and I thought this part was absolute genius, it tracks the premises that your transactions rely on. At the exact moment your transaction tries to commit, the database looks back and asks, has the data this transaction read been modified by anyone else in the meantime? If the premise is now outdated, like in our doctor example where the count dropped from 2 to 1, SSI catches it, aborts the offending transaction, and forces the application to retry. You get the incredible performance of snapshot isolation combined with the perfect safety of serializability.
Section 6. The illusion of perfection.
Let's bring this all together, diving into these deep back-end mechanics and finally grasping the real difference between read-committed, snapshot isolation, and serializability completely changed how I think about system design. Transactions are incredibly helpful, but they are not magic. They are engineered abstractions, and all abstractions leak. The database cannot read your mind, and it relies entirely on you, the developer, to understand the massive trade-offs between system performance and absolute data consistency. You have to actively choose the right isolation level for your specific use case. Do you know what default isolation level your production database is using right now? Because if not, you might want to check it immediately.
I want to leave you with this quote from computing pioneer Alan Kay. He said, "Computing is often treated like pop culture, ignoring the history and theory of the past. To build truly scalable, unbreakable systems, we cannot just rely on pop culture buzzwords like ACID. We must understand the deep theory behind the tools we use every single day." If this explainer changed how you view your database, join us for more deep dives into distributed systems. And it leaves us with one terrifying question. If your database has been silently lying to you this whole time, what other foundational systems in your tech stack are currently holding secrets?